Intro. Welcome to Mechanics of Materials, also known as Strength of Materials. If you're studying mechanical or civil engineering, this course is essential. Why? Because every structure, buildings, bridges, vehicles, needs to withstand forces without breaking. In this course, we'll explore 1. How materials respond to forces. 2. How we measure stress and strain. 3. And most importantly, how we design structures to be safe and reliable. Let's get started. Why structures need to be elastic. You might not realize it, but the buildings around you move, just a little. When people walk inside, when the wind blows, when temperature changes, structures flex and return to shape. This is called elastic deformation, and it's essential for safety. 1. A skyscraper sways slightly in the wind. 2. A bridge expands and contracts with heat. 3. Even the floor beneath your feet bends slightly under your weight. If structures weren't elastic, they'd crack under normal conditions. External versus internal forces. Every structure experiences external forces. 1. The weight of people, furniture, and equipment. 2. Environmental forces like wind, earthquakes, and snow loads. But what's more important is how the material itself responds to these loads. Inside every structure, there are internal forces. These include 1. Shear forces that cause parts to slide against each other. 2. Bending moments that make materials flex. 3. And most importantly, stress and strain. This is where mechanics of materials comes in. What is stress? To understand how materials behave, we need to talk about stress. Stress is simply the force applied divided by the area it acts on. Cephe plus sigma eo plus frac. A. At 1. A thicker beam supports more weight than a thinner one. 2. A large bolt holds more force than a small one. This is why engineers don't just look at force, they consider stress, which tells us how much force a material can handle before failing. Stress is measured in 1. Pascals per in metric units. We usually use MPa or GPa because forces are large. 2. Pounds per square inch, PSI, in imperial units. 3 main types of stress. Structures experience 3 types of stress. 1. Tension, pulling apart. 1. A rope holding a load is in tension. 2. Steel cables in a suspension bridge stretch under load. 2. Compression, pushing together. 1. A building column supports the weight above it. 2. A chair leg is in compression under your weight. 3. Shear, sliding forces. 1. A scissors blade cutting paper is an example of shear. 2. A bolt in a bridge joint resists shear forces. Each of these forces affects how a structure behaves and how we design it. Shear stress shear is a bit different from tension and compression. Instead of pulling or pushing, shear stress happens when forces act parallel to a surface. Tefe plus tayu ike plus fre of 8a. 1. Bolts, rivets, and wood joints experience shear forces. 2. When you tear a piece of paper, you're applying shear stress. It's especially important in connections between materials, like bridges and buildings, real-world applications. Understanding stress isn't just theory. It's how engineers build safe structures. Bridges, suspension cables stretch in tension while pillars handle compression. Buildings, skyscrapers must withstand wind shear and earthquakes. Cars and planes, vehicle parts must flex without breaking under stress. Every piece of engineering is designed with stress in mind. Final thoughts. To sum it up. 1. Stress equal force. Area, larger area, less stress. 2. Different materials react differently. Steel, concrete, and wood all have different properties. 3. Structures must be designed to withstand stress to avoid failure. Next, we'll explore how materials deform under stress and what happens when they fail. Key takeaway: Everything from a simple chair to a massive bridge is designed with these principles in mind. Understanding them is what makes great engineering possible.